Okay, Shantanu, looks like you can get started.
Wait a couple of or a few seconds more. Okay. Hello, everyone, and welcome to the Wednesday, October 28th press briefing here at the DPS. I'm Shantanu Naidu. I'm the DPS press officer. And with us today is also Rick Fienberg, who's the AAS press officer. He'll be helping us with the Q&A and any technical issues that may come up. There'll be a couple of press releases from today's briefings, so please look out for those. In case you missed yesterday's or Monday's briefings and you would like to go online and watch those, you can go to the meeting website, click on press information, and you'll find links for presentations, press briefings, and other things on there. So we're gonna record today's briefing live and also stream it live to YouTube, where it'll be archived for future viewing on the AAS Press channel. I'll first give a brief introduction of all the panelists and their topics. Then the panelists will speak in order, and then we'll go to Q&A. We've asked the panelists not to answer questions via the Q&A box, and they'll answer all the questions later on during the Q&A session. Okay, so there's been a slight change in the press briefing today. We'll have at least 3 speakers. We'll start with Colin Chandler from Northern Arizona University. We'll talk about cometary activity discovered on Centaur 2014 OG 392. Next, we'll have Laura Woodney from California State University at San Bernardino. We'll talk about contemporaneous multi-wavelength observations of the active Centaur 2019 LD2. And then we'll have Jordan Steckloff of the Planetary Science Institute, who'll talk about the physical processes restricting dusty debris disks to cooler white dwarfs. And we might have Humberto Campins of University of Central Florida show up later on. And in case he does show up, he'll speak about new candidate exogenous material on asteroid Bennu, identified with OSIRIS-REx MapCam and PolyCam images. So with that, I'll pass it on to Colin Chandler. You can take over.
Thanks, Shantanu. So hi, yes, I'm Colin Orion Chandler. I'm a graduate research fellow at Northern Arizona University for the National Science Foundation. And I'm going to talk to you about cometary activity discovered on Centaur 2014 OG 392, which is pictured here as a DPS premiere. We took this image just a couple of weeks ago at the Lowell Discovery Telescope, and it is indeed still quite happily active, meaning it's got a tail and a coma. So what are we talking about exactly when we say Centaur? So let's put it in context. This is a diagram of the solar system with the planets going from Mercury on outward, and these are all to scale by size, certainly not by distance. At the outer edge there, we've got Eris and Sedna, and on the innermost, we've got Mercury. And when we talk about volatiles in the solar system, we often think about comets because they're the fuzzy snowballs, they're very active and dramatic. But we also know that there are volatiles. So these are ices, things that sublimate on the surface of asteroids, such as Ceres, shown here. It's also been detected on other objects spectroscopically, and we've seen active asteroids as well that appear to be sublimating volatile materials. In the extreme other end, we have the distant objects, such as Pluto, as imaged here by the 2015 flyby of New Horizons, which certainly has plenty of volatiles on the surface. But today we're going to talk about an intermediate range that orbits between Jupiter and Neptune called the Centaurs. And these are thought to be transition objects that actually originate from the distant objects category over there, region known as Kuiper Belt, and are in this region for roughly hundreds to maybe millions of years, and then they move on to become either Jupiter family comets or get ejected from the solar system or other fates, which we'll discuss in a moment. So how do you go about finding one of these? Well, we actually started with archival data, and we found this image of 2014 OG392, indicated by the dashed red arrow, surrounded by the smudge that is activity. Those are the green arrows. We did have more than one image, so it's not like that was our only clue, but it definitely warranted confirmation rather than taking that at face value. And we were fortunate to be able to get, we took our own images at the Blanco 4-meter telescope in Chile with exactly the same camera, the dark energy camera. And there was indeed something quite suspicious there, again, indicated by the green arrows. Using a slightly larger 6.5 meter Walter Baade telescope, Magellan, we were able to confirm there was indeed activity, and we carried out a follow-up campaign of detailed study at the Lowell Discovery Telescope here in Arizona. So the detailed study involved a number of different aspects, including measuring the coma mass and extent using an aperture or a ring shown here on the left around 2014 OG392. We measured as roughly 2.4 billion metric tons in this coma at extent about 430,000 kilometers. Now, this already gives us a hint, given that we had found archival images of it that indicated it's been active for years, that is probably not a transient event, and this sort of further cements that by showing the level of activity is pretty high. We also modeled the dynamical lifetime or orbital stability of 2014 OG392. This diagram or animation shows the sun in the center surrounded by first the orbit of Jupiter, and then Saturn, Uranus, Neptune, or the concentric circles. And the oval or the ellipse is 2014 OG392, shown colliding with Saturn there, which is actually an outcome in a number of the dynamical simulations that we ran. So that gave us sort of a shorter end of the time scale of 13,000 year stability lifetime, and on the very far end was 1.8 million years. And this gives us some constraints on how long it's been there, and so how long materials would have had to actually leave the surface through sublimation. So take those two pieces of information and combine that with laboratory data, specifically sublimation rates of different materials under different temperatures and pressures. Usually we think of this as like dry ice, as shown here. It is Halloween time after all. So take those three things, synthesize them together, and it seems as though that even at this distance of twice the orbital distance from the sun as Jupiter, that methane and carbon monoxide probably already sublimated from the surface long ago. On the flip side, methanol and water, it's certainly way too cold out there in order for those to be the primary agents responsible for the activity that we see. And so this leaves in the Goldilocks zone of sublimation, carbon dioxide and ammonia. It seems to be the species most likely responsible for the activity that we see on the surface. And so this has some implications about solar system, the volatiles where they are now and where they came from. And so we believe that volatiles are important to life, not just here on Earth, but perhaps throughout the solar system and beyond. And in order to really understand how this works, we'd like to know where the water on Earth came from, where it is now in the solar system. This artist concept of early solar system shows comets coming in, and asteroids delivering water to this interior planet as well. That's a more recently adopted reservoir of volatiles being considered. And we believe there is some amount that was already in place during formation. And it's also believed that some amount was delivered after Earth's formation. The exact ratio is still being debated, and we're exploring that. And in order for us to be able to narrow that down, we need to know what's actually available to us to even deliver in the first place. So we have these additional reservoirs to consider. So maybe we really should be zooming out of this diagram. Jupiter is there in the foreground. And so that's where the Centaur region would start, is right there moving outward. And then we also have some of these icy bodies to think about too, like Pluto. So just as a recap, we found cometary activity on Centaur 2014 OD392, which just as of a couple of days ago was renamed to C/2014 OD392 Pan-STARRS in honor of its discovering the survey to discover the asteroid form. And we know it's been active for a couple of years. You can see this new image on the right. This is also first time being shown. It's a 7,700 second exposure at Lowell Discovery Telescope. And this longer period activity indicates that it's probably not a transient event, such as an impact event. And we independently confirmed this at 3 different observatories. The coma size is roughly 430,000 kilometers. It seems that the orbital stability is around 13,000, 1.8 million years, which combined with its orbital distance of roughly double Jupiter's orbit from the sun, and that tells us that it's almost certainly not water or methanol responsible for the primary sublimation that is driving the activity that we observe. Most likely molecules responsible for the activity we observe we find to be carbon dioxide and or ammonia. And we have more details in a publication that's listed below. And I thank you for your time, and off to Laura. Laura, I think the audio might be having some trouble.
There I am, unmuted. Oops. Let me try to screen share again. So thanks to Colin there for the great introduction to centaurs, because I'm also going to be talking about an active centaur here, one that was discovered in 2019, and it was given a comet designation because it was already active. And but originally it was actually thought to be a active Trojan asteroid, which is an asteroid that is dynamically linked to Jupiter. But my team quickly realized that it was actually a Centaur. And more than that, it's in what we call a gateway orbit, such that it is actively transitioning from being a Centaur, as Colin described for us, to being a Jupiter family comet within the next 40 years. So that makes this particularly exciting, because this is the first time that we've actually discovered an object that we know is going to become a comet within the lifetimes of our graduate students for sure, so that we can observe and watch this object as it transitions from something that produces a coma due to processes that have nothing to do with water ice sublimation to water turning on. And how does that change the activity of the comet? How does that change the composition of the comet? So there's a lot of observing to do as we watch this object turn on. So once my team, led by Teddy Coretta and Jordan Steckloff, who is actually here for talk about something else, realized it was one of these gateway objects that was transitioning, we set up an observing campaign, and we've got time on the NASA RTF telescope, on Gemini North, and the Arizona Radio Observatory, all simultaneously, to see if we could parameterize what this object looks like now. And so I should point out our this orbital modeling done by Coretta and Steckloff, showing that right now, so when you go too far into the past, things get chaotic once you dynamically model into interactions with the giant planets. But we can be reasonably certain that this object has never entered the inner solar system before. So this is really going to be the first time that water sublimation will be turning on for this Centaur that's making its way into the solar system. And so right now we're right here at 2020, and around 2063, the perihelion distance dramatically drops into the inner solar system, and it will be becoming a Jupiter family comet. So what did we see? What have we seen so far? What we see so far is an active object. So these are images from Gemini North. So this object has a coma. We've used pre-covery images, so images taken with Sarah Tololo Dark Energy Survey back to 2015, and this object is there and has a coma. So that this has had a persistently active coma for a while. So while this is not produced by water sublimation, whatever is pulling the dust off, these are images these are reflectance images, so this would be reflected dust. So whatever is causing this coma production is steady state. We have not detected. We don't have any outbursts in our data. So it's just a sort of consistently active object, consistent with being a couple of kilometers in size, just as another group have found with HST imaging of this object. So, so we plan to continue parameterizing this object. We were not able to detect any carbon monoxide gas production. There are several hypotheses for what could be causing this activity in centaurs out where water can't sublimate. And one of them is CO or CO2 outgassing, though that is a little bit hard to believe that could be the only thing, given CO and CO2 can sublimate as distantly as the Kuiper belt. So there really shouldn't be a lot of CO2 ice still remaining on on the surface and easily outgassing, just because it's had such a long time to do that. But another possibility would be amorphous to crystalline ice transition. And there's certainly ice, there should be ice in there will be ice in the nucleus that will be ready to sublimate when it warms up. And we have reflectance spectra of the dust here. And what we see is evidence of, there's a slight evidence, and when you look at the spectra, that we see a couple percent of water ice crystals in the reflectance spectra of the dust coma. So ice is certainly there, and we look forward to having it turn on. So one thing we have done is, because we want to encourage the community to observe this object, watch it become a comet, we have set up an observing campaign. So we have an observing campaign that we are in the process of setting up. What we want to do is facilitate the community talking to each other, coordinating their observations, doing more of these contemporary observations so that we can learn as much about this object, learn as much about its composition, learn much about what its dust is like, so we can observe the changes that happen as it transforms to being a comet, and therefore learn about the processes. What are the differences between centaurs and active comets? What can that tell us about the formation of the solar system? How can that inform us about interpreting our cometary data when we're using it to draw conclusions about solar system formation processes? So we think this is a really exciting object. We know it's a really exciting object, and hopefully the whole community will be getting on board with observing this object, observing the birth of a comet. Thank you.
All right, Lori, do you stop screen sharing?
Oh, yes.
It looks like okay. Looks like someone's turned off my video, but that's fine.
I'll mute.
Okay, 1 sec. Okay, I think we're rolling, right? Okay. So hello, I'm going to be changing gears a little bit from the centaurs that have been discussed so far, but I promise there's actually some very similar physics here. It's strangely all of these topics tie together in kind of a fun way. But I'm going to be talking about the physical processes that control and restrict dusty debris disks to cooler white dwarfs. So to start off with, what is, there is a lot of text there, I apologize. So what is a white dwarf star? Well, at the end of a typical sun-like star's life, the star will expand out and become utterly massive, as we can see on the left here, to a size that's comparable to the size of the orbits of the inner planets of our solar system, meaning that our home, Earth, and the other planets in the inner solar system will be swallowed up by the star and be more or less destroyed as we start orbiting inside of the star. But this red giant phase does not last forever. Eventually, the sun in its death rattle will ultimately collapse into an Earth-sized remnant, effectively a hot glowing ember that's approximately the size of the Earth. And these are what we call white dwarfs. They are massive, comparable to the mass of the sun, or about half the mass of the sun, but the size of a terrestrial planet like the Earth. As a glowing remnant, the spectrum, how much light these white dwarfs put out in each color, is generally pretty predictable. It's what we call a black body spectrum. Things like glowing stoves, anything that's just hot and glowing, that's a black body. And so when we look at a white dwarf, we can look at its spectrum, and based on the shape of this black body curve, we can figure out what its temperature is, and we can figure out how big / how bright it is. And this is generally what we expect to see. And as white dwarfs age, they cool down. And so what we expect over time is to watch these spectra slowly cool as the white dwarf loses its remnant heat. But about 4% of white dwarfs have a pretty significant deviation from what we would expect to see. Instead of having a nice uniform black body spectrum, we find that at the longer wavelengths, in the infrared, there is an excess of light. And this can't be explained just by a black body alone. This seems to be the signature of a bunch of material that's being warmed by the remnant heat of the white dwarf and contributing to the spectrum. And this is why we think that white dwarfs have these dusty debris disks. We can't see the disks themselves, but we can see the signatures of these disks in these spectra. And so the question is, how do these debris disks form? One would expect that during the red giant phase of the star, anything in that inner system should be destroyed. And so these materials have to migrate inwards from further out. And so there's this two-step model that's thought to explain it. Step one, we have an asteroid that gets scattered, gravitationally flung toward the star. And if it gets close enough to the star, the tides of the white dwarf itself will break it up into dust. And then radiative forces, such as Poynting-Robertson drag, will circularize their orbits until they have a bunch of dust orbiting in a nice, uniform, tight debris disk. And this this seems to make a lot of sense, but it also makes some predictions. One thing we would expect then is for if this two-step model is correct, is that white dwarfs that are hotter, that have stronger radiative forces, can circularize dust much more quickly. And if they're younger white dwarfs, they may have less stable planetary systems due to the giant branch phase, the red giant phase. And so we would expect more asteroids to get scattered inwards. And so we would actually expect warmer white dwarfs to preferentially have more of these debris disks relative to cooler white dwarfs. But what we see is actually the opposite. We see that there are absolutely no young white dwarfs that have dusty debris disks. And it's only after the white dwarf has cooled tens of millions of years until its temperature is around 27,000 Kelvin that we start to see debris disks form. And so we wanted to understand why is what we observe the complete opposite of what we would expect? Does this tell us there's something wrong with the two-step model in the first place? And so we wanted to look at the physical processes that are controlling the formation of these debris disks. As we discussed earlier, one of the critical processes for forming debris disks is tidal breakup. What we need is for the initial asteroid to get so close to the star that tidal forces are strong enough and can break the object apart. If it's too far away, then gravity of the asteroid itself will hold it together. And so this is called the tidal disruption radius, or the Roche limit. And I'll be referring to the Roche limit. So we need the asteroid to pass inside of the Roche limit. And what we discovered is that there's a second process that hasn't been accounted for that actually imposes another constraint on the formation of dusty debris disks. And that is, if the asteroid or the dust gets too close to the white dwarf, it will get so hot that it'll immediately begin to vaporize or sublimate away. And so what we need then is for the asteroid to be outside of this sublimation radius. It needs to be far enough away from the star that the resulting material doesn't get so hot that it vaporizes. So this imposes two constraints. We need the asteroid to be both outside of the sublimation radius, yet inside of this Roche limit for a dusty debris disk to form. And so what we find then is, and the other critical thing is that as white dwarfs cool, the sublimation radius recedes inward. Because as the white dwarf cools, you have to get closer and closer to it for vaporization to be effective. And so around young white dwarfs, the sublimation radius is very large and greatly exceeds this tidal disruption radius. So what this means is that if a dusty debris disk were to form, or if an asteroid were to pass inside of the Roche limit, the material would more or less immediately vaporize. And so we want to know then is, how cool does the white dwarf need to be such that the sublimation radius passes inside of the Roche limit and gives us a region of space where dusty debris disks can stably form? Because if once the debris disk cools far enough, we can see on the right side of this figure that the sublimation radius is inside of the Roche limit, and so there's a space between the sublimation radius and the Roche limit where asteroids can pass, tidally disrupt, and then ultimately form dusty debris disks. So we wanted to explore what is this critical temperature. And what we found is that this critical temperature for most asteroidal materials happens to be between 25,000 and 32,000 Kelvin, with some materials having even closer fits to the observed 27,000 Kelvin. And this is just using typical asteroidal materials that we find here in our own solar system. And so this agrees pretty well with the observations. And so what we think this is telling us is that there's an additional constraint, that the receding sublimation radius is the reason why dusty debris disks only form around cooler white dwarfs. If they were to form around a warmer white dwarf, the solid materials would immediately vaporize. And this shows that there actually isn't a problem with the two-step model. And in fact, this restriction of 27,000 Kelvin is actually evidence of the two-step model and is broadly consistent with it. And finally, this observed limit suggests that the materials we're seeing orbiting dead stars in other planetary systems is actually pretty similar to the stuff we find in our own solar system, drawing further parallels between exosystems and our own. And with that, I will hand it off to Humberto.
Okay, I hope you guys can hear me.
Yep, we can hear you.
Okay, can you see my presentation?
Yes.
Okay, good. I am presenting from one screen and talking from another. The joys of Zoom. Okay, so there's a paper that came out in Nature Astronomy in September, on September 21st, reporting the identification of 6 boulders on asteroid Bennu that were composed of pyroxene and were identified to be closest to asteroid Vesta and the Vesta family and the HD meteorites. So, this new we've identified beyond those first 6 boulders, we've identified about 77 boulders. This is a little bit dated, and we have analyzed 44 of them. And so this exogenous material has been reported on Bennu and Ryugu. And in the case of Ryugu, they look more like ordinary chondrite material than the HED meteorites that have, that we have identified on Bennu. So the bright boulders were identified on asteroid Bennu. We use the red slope in the 4-color spectrum in the MapCam images, and we used an absorption near 1 micron as a way for us to identify these candidates. And we are in the process of comparing them with the reported results from Ryugu. So the exogenous boulders, that slide that just went by, this went into an automatic presenting mode. I don't know why. In any case, the new candidate exogenous material, we use MapCam images for the color, and we use the PolyCam images for the more detailed morphology of these objects. These boulders that we have identified have included the 6 that were identified in the Della Justina et al. 2020 paper that just came out about a month ago. And we have the identified boulders are distributed around the surface, as you can see in this map. We excluded incidence and reflection angles of more than 70 degrees, and therefore we excluded the polar regions of Bennu. And so the exogenous materials that the candidate exogenous materials we have identified are preferentially in the most rocky regions of asteroid Bennu. As you can see here, the material can be either single rocks on the left or inclusions on darker rocks. So the hypothesis is that these were objects that impacted the parent body of Bennu and ended up on Bennu once the catastrophic disruption occurred and Bennu formed. And so there is some correlation between their morphology and their spectra. The bright boulders with reflecting spectra peaking at 0.55 microns have lower than normal albedo than the other candidates, suggesting a different composition. Our initial composition comparison with asteroid Ryugu indicates that Bennu has a lot more abundance of exogenous material than Ryugu, and so far the composition of the exogenous material on Bennu appears to be different from that of Bennu, although we might be able to identify new ones in this process. So we have started a further analysis of the MapCam and PolyCam images from the OSIRIS-REx spacecraft, and they have revealed a wider diversity of potentially exogenous lithologies on Bennu than that reported by Della Justina et al. And we continue our study of this diverse material on Bennu's surface, which can constrain the asteroid's origin. There is an abstract by Baluz et al. that discusses how our observations can constrain the collisional history of this asteroid.
Okay. Thank you to all the presenters for presenting their slides. If you can turn on your videos again. And we'll take questions, which, as I mentioned before, you can click on the Q&A box down there and ask any questions, and Rick will read them out.
All right, we do have a few questions queued up. So the first one comes from Rick Lovett, a freelancer out on the West Coast. This is for Humberto. Is there a chance that OSIRIS-REx might have scooped up a small bit of one of these exogenous rocks? And if so, how would we recognize what it is when it gets back to Earth?
That's an excellent question, Rick, and we sure do hope so. It is very likely that as this material breaks into smaller pieces, it has been distributed throughout Bennu. Our identification is limited to the very largest objects because of the resolution of the camera. But we're actually going to be looking at the images of the region where the sample was obtained, which is called Nightingale. And it will, we hope so. And in terms of identifying it in the sample, which seems like we got a very abundant sample, is they would be identified from their composition. These are mostly olivines and high albedo, and they are, we're hoping that Bennu will have these throughout the surface, and they will be in the sample, in which case the OSIRIS-REx mission will be a sample return mission to both Bennu and Vesta.
Great, thank you. Here's a question, another question from Rick Lovett. This one could be for, probably for Colin or Laura, I would think. Why are these objects called centaurs, and when were they identified as a separate group?
I could take this. I just went down this rabbit hole not long ago.
Great, thank you.
Okay. So it's a good question, and it's hard to find the answer. IAU naming is kind of famous for being a little bit interesting. So it turns out that the idea is that we want to have objects in the Centaur category are named for things that are shape-shifting or hybrid objects. And so that's the idea behind having a combined horse person. The first one wasn't realized until after the fact. It was actually Hidalgo in 1920 by one of the Centaur definitions, and there are several. And 1977, though, is when the category was actually conjured up as a group by 2060 Chiron, which is a centaur, mythical centaur. For the active centaurs that Laura and I were talking about, the first one is really 29P, Schwarzman and Walkman 1 from 1927, and then Miss Oterma in Finland found one during 1942, actually wartime, which is super impressive. And that was the second one, and that's actually transitioned since then. Yeah, so that's it in a nutshell.
Great, thank you.
If I can just piggyback on that, because Colin did a really nice of saying, like, you know, what is the naming scheme? The reason that these things are named after chimeric objects is that the centaurs themselves seem to have a similar dual nature. Just as the centaurs are half horse, half human, the centaurs in the sky seem to sometimes be asteroid-like and sometimes be comet-like. Some of them, in the comet-like ones, we call those active centaurs. The centaurs themselves are a dynamical class, but they're called the centaurs because members of the class seem to exhibit this dual nature.
Great, thanks for that. All right, the next question is from Bob Buchheim. He's an amateur astronomer out in California. For Laura Woodney, do you have a forecast of the integrated visual magnitude of LV2 over the next few years? Can you tell us whether we have any shot of seeing it from our backyards?
Ooh, that is a good question. I am not prepared for that question. Let's see if I can quickly. You know what? That is something I can, I can get back to you with, if you give me a little bit to calculate that. But yes, we can certainly come up with that.
Okay, that's great. If you let me know,
Mhm.
let me and Shantanu know, then I can add a note in the press kit
Okay.
so that people can come back and refer to it later. Okay.
Okay, we'll do.
Or you can even add a slide to your presentation
Okay.
and then send me that. Great, thanks.
Mhm.
Okay. Next question is from Irene Klotz, who's writing for Aviation Week in Space Technology. Why do you think Bennu has potentially more material from its parent body than Ryugu does? I guess that's for Humberto. Why do you think Bennu has potentially more material from its parent body than Ryugu?
We don't know if it's more material from the parent body. We don't know what the collisional histories of these two objects are, but we are going to be using these observations to constrain just that. For example, there's a lot more material from the breakup of Flora, which is an ordinary chondrite family in the innermost part of the belt, that is permeating the entire inner belt. So why aren't the big pieces that we detected initially on Bennu not ordinary chondrites, but Vesta material, even though there's more Flora material than Vesta? It could very well have something to do with the timing. So when the Vesta family was created from impacts on what we now see as the Veronea and Rhea Silvia craters on Vesta, they may have coincided with the formation of Bennu, or the parent of Bennu, more closely than the arrival of the Flora material, which could have been later. So it is not that it has more material from the parent body. It is more likely that what the timing of the disruption of the parent body was. And it could very well be that the Polana family, which is statistically the more likely parent family of Bennu, was broken up and created by a Vestoid.
Okay, don't go away, Humberto, because we have a couple more questions for you. Another one from Rick Lovett. What is the significance of this overall to our understanding of the history of the solar system?
Some of it comes from what I just said. Maybe we can constrain the timing of the formation of Bennu and Ryugu from the composition of these exogenous materials on the surface. The other one is that until recently, it had been believed that the impact or the projectile would, in a catastrophic disruption, would be vaporized. And so theorists had been telling us, don't even look for the projectile in your families because it's not going to be there. Well, the Amhatasita meteorite indicated that there could be at least 5 different lithologies, 5 different parent bodies in one meteorite. That means that there had to be 5 impacts that were not erosional, but they were accretional on the parent of Amhatasita, which was 2008 TC3. Now, this is the first case when we discovered an asteroid above the atmosphere. We followed it in. We were able to recover the meteorite, and it turned out to be a very strange meteorite. Statistically, one would think it would be an ordinary chondrite, approximately 80% of the probabilities just from our collections, but it turned out to be mostly uralite, but with ordinary chondrite, 2 types of ordinary chondrites, enstatite chondrites, carbonaceous chondrites, and maybe other lithologies in it. And I've always thought that that was very strange, that the first time we see something like that in so much detail, it turns out to be so weird. So it makes me think that these objects are more common. It made me think back then that these objects were more common than we thought. And that the statistics were skewed by some kind of a bias. And it turns out that the discovery of exogenous material on Bennu and Ryugu are indicating that that's the case. And even before that, the discovery of primitive material, hydrated material, dark material on the surface of Vesta is also contributing to this. So this is telling us that the impacts that create these objects are different from what we had anticipated, and the survival of the projectile is much more likely, as we have demonstrated now on Bennu, Ryugu, Amhatasita, and in the case of the dark material on Vesta. And it is going to help us understand and constrain the collisional evolution of the inner belt, and the fact that maybe these original collisional models that we had about how frequent and what the average velocity of impacts in the inner belt would be might have to be revised. Or that, for example, what happens when you have glancing impacts, which are much more common than straight on.
That was a very nice answer, and I think you may have included in it the answer to this next question from Rick Lovett, which was, you said you'd predicted this kind of thing long ago. Can you elaborate now?
Yeah, I was almost chased out of the OSIRIS-REx science team meeting by all these meteoricists that were telling me Amhatasita is a very weird, unlikely event. Don't bother us with predicting bright objects on Bennu. Go away. But a few of them did take me seriously, including Dani Della Justina, the head of the imaging team, and she discovered these exogenous materials as bright objects on Bennu. But the point is, I had been warning the team that we could have very dark and bright objects on Bennu because the orbit of Bennu is similar to the orbit of 2008 TC3. They are both most likely to have come from the Polana family in the inner belt. And if they both came from the same family, they could have similar characteristics on their surfaces. And the other thing to remember is that we have the Amhatasita meteorite, which is approximately 0.1% of what entered the atmosphere as 2008 TC3. So we lost 99.9% of the material. And what was that? Was that carbonaceous? Was that a different type? Was that the most fragile material? That's the big justification for a sample return, of course. But in addition to that, we need to start thinking that our initial assessment of Amhatasita being, 1 in 5,000 or 1 in 10,000 occurrence may be a lot more common. And so that is what motivated me to predict this and say that we would find what I called at the time xenoliths or exogenous material on Bennu, which we have on Bennu and Ryugu.
Great. Okay. Well, that's it for the questions that were in the Q&A box. So unless we get another one in the next 30 seconds or so, I think we're able to wrap up a touch early today.
Okay. Thank you to all the panelists and the attendees, and also all the PIOs behind the scenes writing the press releases, helping with the press releases for this wonderful press conference. We'll see you tomorrow, but a reminder that we start 15 minutes earlier than today. So we'll see you tomorrow at 10:45 a.m. Eastern Daylight Savings Time. Thank you, everyone.